Yeah. So G path queries. You've been given a tree in which you have to get the answer of the number of pairs of vertices that does not exceed the query QI. There are m queries and n vertices and minus one edges and both 25. So we have to get a time complexity of at least n log n or something. So um, how do we solve this? So for that, before we get to approach, let's first see what you would do for a query like this. How do we get an answer? What we are getting right now. So we are getting an answer of this, right? We are getting this answer for the following query. We are getting this answer. How do we get that? So let's start with the one. For one, we are getting three. How do we get? How do are we getting three? Let's see that. Um, So this is one edge that is of one maximum weight. This is one edge that is of one maximum weight. And there are no other edges, right? So the question says, what are the number of pairs of vertices that when you make a path from U to V, the maximum weight that we get when we make a path from U, let's say suppose this is U and this is V. So when we make a simple path from U to V, we get a maximum weight of the query QI. So this it satisfies that, right? So the number of vertices that you can see here are three because one pair is 1, 2 and one pair is 1, 4. So that's the answer. So we get how we arrived at 3. So let's take a better example. Let's go to 2. How do we get 7 for the query 2? So for the query 2, you have this edge as well and this edge as well. But here we can see that from 1 we can go to 2, from 1 we can go to 4, from 1 we can go to 5, and so we can go to from 2 to 4, 2 to 5. So we can see that we can make n c nc two number of pairs considering this is n. And what is n here? N is equals to 1, 2, 3, 4. 4. Okay. And here for the edge 3, 6, since we can't reach from 1 to 4 or 5 to the edge 3 or 6, these pairs will be independent. So we will get an answer 1 from here and 6 from here. Okay. That makes up to 7. After this, let's talk about 3. For 3, we are getting 15, right? So another edge gets added, this edge. Now the whole thing becomes 1 because now we can reach from 1 to 4 and 5 to the edges 3 and 6. So um, the disconnection or the independent sets have now become 1. And how many vertices do we have in this whole tree? We have 1, 2, 3, 4, 5, 6, 6 vertices, right? So the answer comes out to be 62. Got it? After this, let's talk about the test case 4, or let's leave it. So we can see after we get the query 4, we will have all the edges in it, and for 6c2, instead of 62, we will have a value of 7c2 as the answer. That is 21. How can we see that? 7 into 6 divided by 2, that is 21, right? So 7c2 is the answer here as well. And yeah, that is how the answers are coming. Now, talking about our approach, we can see that we have to initially make like the connected components of stuff, and we have to count how many vertices do each of them have, and for each query we have to calculate the nc2 values of each of them. So essentially we have to calculate something like ni nic2 nic2. Isn't that true? Second, nic2. So this is not working as I suppose it would. So you get the picture, right? NiC2. So NiC2 is what we need to calculate. After this, since we have to calculate NiC2, we can think of DSU, not because of the NiC2, but because of the number of connected components that we have here. We have to calculate here, right? So we think of DSU. And in the case of DSU, what do we think? We have to compute m queries and n number of edges as well are there as well, and we have to compute m queries as well. So we can't think of a solution in which the iteration runs again and again on the whole tree for each query. So why don't we construct the graph as we are moving forward with the queries that we are taking? So, and how are we taking the queries? We are taking the queries as like 5 to 3 4 1. This is not an ordered pattern, anyways. But let's say we sort the number of queries in a sorted manner from like the smallest edge to the biggest edge, biggest weight. After we have done that, like let's take an example. Let's say that we have sorted the edges from like 1 2 3 4 and 5. So after we have done that, we can essentially just construct the graph, the tree for the edges that are less than equal to 1, because that is what we need. We have to construct an edges for like the we have to count the number of pairs for like with the maximum weight 1. So we will basically make a graph, make a tree with edges that have a maximum weight up to 1. So we will do for 2, so we will do for 3, so we will do for 4, and so we'll do for 5. What you can see here is when I illustrated the first test case, um, I only highlighted the edges with 1. That is what is essentially happening here when we are constructing the constructing the tree for only maximum weight 1. So after we have done this, the maximum weight 1 graph, 1 tree has been constructed. We will basically iterate on the parent array of the DSU, and after we have iterated on the parent array, we'll count the values of like NC2, NC3, NC2, MC2, etc., etc., and we will get the answer. So now, since we are iterating on the parent array again and again for getting the value of NC2 for each of the sets. That gives us a time complexity of n into m. That is something we can't afford. So this is not correct. But what if we transform our union function somehow, and our union function, whenever we call it, it automatically changes the current value to the newer value. Like if there are two sets, let's say A and B. A and B are two sets. So if A and B are two sets, first of all, A will have, let's say, n number of children within itself, and B will have m number of children within itself. Now, when we are merging both of them, what we have to do is that since n plus mc2 is the new value, we have to first subtract the value that we get from nc2, and that is already added in the value, that the current value, it is already added. So we have to first subtract it, then subtract this value, and then we have to add n plus 1 mc2. Okay, so that is what is going on, and this is essentially the whole concept and whole thing that we are going through. I will show you the code now, and if you have any problem regarding the code or regarding anything here, please let me know in the comments. And till then, now let's see the code. Okay. Okay, so um, let's start with the let's start with the normal DSU thing. So we take the input here, we take the input, everything is fine. We have like edges UV and the weight. So we sorted everything with respect to weight since we want to construct a graph as per the query that we are getting, right? So we sort all of it. And after that, we take the queries and put. And queries are taken in the form of like A and I because we want to print the vector as the answer. So when you are printing the vector as the answer, we want the answer to be at a particular index. So we are storing the index as well, and we sort all of it. And after that, we have the index and everything, and the parent array as well. So we will construct the parent array for the DSU to work. After that, see, as we are iterating, we union two edges as we are iterating, and the following as we are iterating on queries. I dot first, what is I dot first? I dot first is the weight. So weight of the maximum weight that is allowed. So while that maximum weight that is allowed is not exceeded, we union the edges that are possible. And after we have done that, we take a global value VL, and we change that after every union operation. So we will see how we are changing it. Just a second. See, um, here. So this is basically the union part, right? So here, what's happening is that a parent A plus equals to parent B. This is how I have represented the parent. Okay, talking about how I'm representing the DSU, there might be a place of confusion here because I haven't like really told how I use DSU. So basically, we will have -1, -1, -1 for each independent set. Okay. If you're merging two sets, let's say the first zeroth and the first index, then the one of them will become -2 and the other will become 0 and there. So basically the negative, the minus and represents that there are a number of children in that set, essentially. That's the thing I want to say. And now what's going on is we have two values A and B. So A will have a PP number of children in it, and now I have increased the value of A because A is the parent, B is getting inserted in A. So parent of A is increased by parent of B. So the new value that is parent of A here, this is the new value. Okay, n plus m wala value. N plus m value is this. After that we subtract the old B value and the um, old A value. We subtract both of them and we add this, and also parent of B is then defined again to like equal to A because the parent of B we want it to point to A, right? So we return true, blah blah blah. That is the code. Nothing else is happening here. That's all. So this was a 1800 question. I hope you like the solution. If you have any queries, please do let me know in the comments, and that's all. Thank you.